All right, everybody, take a deep breath. We're Laplace transforming, if I could make that a verb, different functions. You'll see why later. It's going to fit into the context of our non-homogeneous second-order differential equations. But we need to get through this Laplace transform stuff so we can use it later on. We'll build a library, and then we'll just refer to that library. So these things that we're doing now is a one-shot deal. So we've Laplace transformed over here the constant 1 to create a function 1 over s. We will Laplace transform a power of t to get a function of s. E to the at to get a function of s. We're now going to go sine of at. We're going to transform the sine of at to produce a function of s. And to do so, we're going to run it through the Laplace transform. It's always the integral from 0 to infinity of e to the negative st. Thank you, Laplace. Times the function that you want to transform, f of t, in this case is sine of a times t. Now to do that, let me just kind of put it over here. The integral of e to the minus st times the sine of a times t dt from 0 to infinity is what we're going to work on. And as you'll see, this integral is a little bit messy. So to make my writing on my wall here a little bit better for us, I hope, is I'm just going to replace the integrand here with a red box, because I'm going to have to write it a zillion times here, and so I don't want to do that. So just keep in mind that as we go forward, the integral of e to the minus st sine of at is going to be in a red box. So we're going to integrate from 0 to infinity the red box. Now, to do this integral requires good old formal integration by parts. It's not one of those nice tabular ones, because the tabular ones work when you can take a derivative down to 0 and have an ending place. Neither of these two factors will differentiate to 0. So we unfortunately, or fortunately if you like this stuff, have to go good old school integration by parts. Let me remind you, if you have a u part and a dv part, then you can integrate by parts by saying u times v minus the integral of v du. My Calc 2 students like to call this ultraviolet voodoo. Somehow it comes out that way, ultraviolet voodoo. So let's do it. Let's let u equal some stuff. So we're going to let u equal the e to the minus st. And we're going to let dv equal the sine of at. Now when we do that, remember these are s's, not 5's. So the derivative of u, du, the derivative with respect to t is going to be e to the negative st. The derivative of negative st is negative s. So the derivative is there. If dv is sine, then let's see, we're going to need a cosine. The derivative of cosine is going to be negative. The derivative of at would have been a, so the 1 over a to get rid of that. There we go. So the integral in the first iteration here is going to be u times v. So if you don't mind, I'll put negative 1 over a first, e to the minus st, cosine of at, minus the integral of v du. Now negative times a negative, positive. Do you see the s over a? E to the negative st, cosine of at dt. Remember, all s's. There are no 5's here. They're all s's. So there we go. So in our first iteration, we end up with this. Now, this integral, you'll notice, is very similar to where we started, except the sine now is a cosine. So we must integrate by parts once again. Now, we could, and we should, for convenience really, take that s over a coefficient and let's pull it out front. So really we're just going to integrate e to the negative st cosine of at dt. And we're going to do that integral by parts once again. Let me come down here and get the different parts. We'll let u equal e to the negative st like we did before. I mean, it worked so well. Let's just do it again. Therefore, du is going to be e to the negative st, the derivative of the stuff, negative s, dv now is going to be cosine of at. So v is going to be the sine of at. But wait, the derivative of at would have been a, so we need to get rid of the a, with the 1 over a. So, the integral of that stuff in red is going to be the negative 1 over a e to the negative st times cosine of at that we got from the first time, minus s over a times this integral, which is going to be integrated by parts, u times v minus the integral of v du. Let's do it. U times v. Do you see the 1 over a e to the minus st sine of at? Yeah. Minus the integral of v du. Now, do you see the minus s over a e to the minus st sine of at dt, oh, I lost my dt there, dt. Yeah. So, an important note here. Remember, this is the integral of that block in red, and that block in red was e to the minus st sine of at dt. E to the minus st sine of at, there it is again, in red. This is actually a good thing. Watch what happens here. Minus 1 over a e to the minus st times cosine of at minus, hey, I'm going to distribute that s over a. So it's going to be minus s over a squared e to the minus st sine of at. Okay, now be careful here because with all those minuses, things can go crazy. We have minus times a minus times a minus. So it's going to be minus s over a, s squared over a squared, and then the integral, all that red stuff again. So the integral of that red stuff is equal to all that stuff and then another integral from red stuff. Now, if you took Calc 2 and you did this, I hope, in Calc 2, this should be maybe somewhat familiar. I'm going to come back over here because I need some more room. Watch what happens now. See this minus this constant times that integral? We're just going to add it over to the other side. So when we add it over to the other side, we'll have s squared over a squared times the integral of that red stuff plus the integral of that red stuff is equal to negative 1 over a e to the minus st cosine of at minus s over a squared sine of at. Now let me just make sure that you are all good on what just happened there. I took this minus this coefficient or this constant times this integral and I added it to this side. There it is, plus the integral that was already there. All right. Now, it's going to be useful to us to pause here for a minute, because remember, all of these integrals are from 0 to infinity. And even on this side, the integration that we had done, really we should evaluate from 0 to infinity. And it's just going to make our life a little bit easier if we do that on the right side. Let's do it. As t goes off to infinity, e to the negative infinity, 1 over e to the infinity. So the denominator here is getting huge. As t goes off to infinity, cosine curves just go up and down, up and down, up and down. And so that thing goes to 0 minus. Likewise, here, as t goes off to infinity, what did I lose there? Look at that. I lost my e to the minus st. I knew I did. Likewise here, as t goes off to infinity, this thing just goes off to 0. When t is 0, e to the 0 is 1. Cosine of 0 is 1. That's minus 1 over a. As t goes off to 0, e to the 0 is 1. Sine of 0 is 0. That thing just goes to 0. So on the right side we have 0, we have 1 over a. Now on the left side over here, notice we can kind of treat that integral like a variable, like a thing. And so if we factor out that integral, we would have s squared over a squared plus 1 times that integral. Let me pause there and make sure you see it. That integral gets multiplied by s squared over a squared to get this one. That integral gets multiplied by plus 1 to get this one. Remember, the goal is to figure out what that integral is. So the integral of that stuff in red is going to be equal to 1 over a divided by there it is. Remember, this stuff in red was the Laplace transform, e to the minus st sine of at dt from 0 to infinity. Now, we're not going to leave it in that form. Let me come over here because I'm going to get it here in a minute. But let's get over here and make it look a little bit prettier. What we have is 1 over a divided by s squared over a squared plus 1. Let's make that look a little bit nicer. Do y'all believe that 1 is the same as a squared over a squared? And so what we have is 1 over a over s squared plus a squared all over a squared. Now, fraction divided by fraction. Let's invert and multiply. Look at that. The Laplace transform of the sine of at after all that work is just a over s squared plus a squared. It's just a over s squared plus a squared. Whew. All right, I've had enough. So what I would like you to do is you do this one now. You've got a nice model for how it all goes, but will you try, I don't know if I've done a nice job, but as nice and neatly as you can on a piece of paper, will you Laplace transform the cosine of at, scan that thing to PDF and throw it up on Canvas so I can see that you gave it a go. You try it.